When you shine a light through a specific shape, you expect the shadow to match. If you cut a triangle into a piece of paper and hold it against the ground, you see a sharp, perfectly defined triangle of light. But the geometry changes if we slowly pull the paper upward, away from the surface. As the distance increases, the sharp corners of the cast triangle begin to blur. The straight edges bow outward and the angles soften. Theoretically, changing the distance from a light source shouldn't alter the fundamental shape of a shadow. A triangle should remain a triangle, yet this light is morphing into an entirely different form. This effect isn't specific to triangles. We see the exact same result using a square cutout. Held close to the wall, the shadow has crisp 90-degree edges, but as the paper moves away, those corners immediately begin to melt. Regardless of whether the initial hole is a square, a star, or a jagged rip, the projection eventually settles into a perfect, uniform circle. The physical outline of the hole is no longer the defining factor. At this distance, the geometry of the gap loses its influence over the light passing through it. Once we reach a certain distance, the light on the ground stops behaving like a shadow cast by the paper. You are looking at a direct, literal projection of the light source itself, the sun. This is the pinhole camera effect. The tiny opening acts as a restrictive lens. Light rays from the top of the sun pass through the hole and hit the bottom of the projection, while rays from the bottom hit the top, creating an inverted image. Because the sun is a sphere, the resulting image is a circle. The roundness of the star dictates the shape on the wall, overriding the physical shape of the obstacle. The reason this only happens at a distance comes down to how do light rays diverge and travel through space. When held extremely close to the ground, light rays hit the surface immediately, allowing the square shape to remain dominant. But as the surface moves further away, the diverging rays have room to fan out, creating overlapping circular projections that blur the square's edges. At a sufficient distance, overlapping solar images completely wash out the original shape of the hole. A shadow's final form is a mathematical contest between the shape of the obstacle and the shape of the light source. Over a long enough distance, the light source wins. This same geometry appears outside the lab, scaling up to the massive natural structures in our everyday environment. In a large tree, the jagged, irregular spaces between overlapping leaves act as thousands of microscopic pinhole cameras. As the sunlight filters through the canopy, it projects tiny, perfect circles of light onto the forest floor. You can see these distinct, glowing shapes scattered across the ground, mimicking the paper experiment on a massive scale. The soft spots of light on the sidewalk are thousands of individual solar images, literal projections of the sun scattered across the ground. To see how the light source defines these shapes, we can look at a theoretical thought experiment. Imagine a solar system where the central star is shaped like a giant triangle instead of a sphere. A moment of wonder. On Earth, every pinhole, every leaf gap, and every square cutout would suddenly project distinct glowing triangles onto the ground. The shapes we see in the light around us are not defined by the physical objects blocking the sun. They are defined by the geometry of the star that creates them.